Lions have a hunting success rate of about 25%. Wolves sit around 14%. Cheetahs, the fastest land animal alive, manage roughly 58% on a good day. Dragonflies catch their prey over 95% of the time. That makes a 2-inch insect the single most successful predator on the planet. And the way they do it is unlike anything else in nature. They don't chase. They calculate exactly where their target will be, and they intercept it mid-flight, adjusting their trajectory in milliseconds. This insect is older than dinosaurs, and 300 million years of evolution never found a better design. A dragonfly does not hunt the way you think a flying predator hunts. Hawks spot prey, dive and close the gap from above. Bats echolocate and intercept moths on the wing. Even other fast insects rely on reaction, changing course when the target moves. Dragonflies do none of that. They use a strategy called predictive interception, and until recently scientists assumed only vertebrates with large brains could pull it off. When a dragonfly locks onto a mosquito or a midge, it does not fly toward where the prey is. It flies toward where the prey will be. The dragonfly computes its target speed, direction, and altitude, then plots a collision course that arrives at the same point in space at the same time as the prey. In controlled lab studies, researchers bet dragonflies initiated this interception within about 50 milliseconds of spotting a target. 50 milliseconds. You cannot blink that fast. The mathematics behind this are genuinely unsettling. The dragonfly maintains what researchers call a constant bearing angle. Imagine drawing a line between the dragonfly and its prey. As both move through the air, the dragonfly adjusts its flight path to keep that line at the same angle relative to its own heading. As long as the bearing stays constant, the two paths converge. Submarines use this method to intercept ships. Fighter pilots use it. And a creature with a brain smaller than the head of a pin figured it out about 300 million years before humans invented trigonometry. The success rate in lab conditions reached 97%. In the wild, where wind, rain, and clutter factor in, researchers at the Natural History Museum in London still document rates above 95%. Compare that with any vertebrate predator on Earth, and the gap is enormous. Great white sharks succeed about half the time. African wild dogs, considered the best team hunters on land, average around 80%. A dragonfly hunting alone outperforms them all. So how does a brain with roughly 1 million neurons run a targeting algorithm that's sophisticated? Researchers found the answer in a group of 16 specialized neurons in the dragonfly's brain that form a dedicated pursuit circuit. These neurons track the target against the visual background, filter out distractions, and send motor commands directly to the wing muscles. There is no conscious deliberation. The entire system from visual input to wing correction runs on a closed loop so tight that the dragonfly can adjust its flight path while the interception is already underway. Prey that makes a sudden turn gets tracked and re-intercepted before it has covered more than a few centimeters. The circuit is small, fast, and ruthless. But the targeting would be useless without the eyes to feed it. A dragonfly's compound eyes contain up to 30,000 individual facets called ommatidia. Each one collects light from a slightly different angle, and together they assemble a mosaic image that covers nearly 360 degrees. You cannot sneak up on a dragonfly. It can see you approaching from almost any direction without turning its head. The resolution varies across the eye. The upper portion is tuned for detecting small, dark objects moving against bright sky, which is precisely what a flying mosquito looks like from below. The lower portion handles the cluttered background of vegetation and water. Researchers have discovered that dragonfly eyes contain between 4 and 5 different types compared to 3 in humans. Some species can detect ultraviolet light. Their color vision is among the most complex ever measured in any animal. There is also the speed of processing. Dragonfly photoreceptors can respond to light flicker rates well beyond what human eyes detect. Where you see a continuous stream of light, a dragonfly sees individual pulses. A fluorescent office light looks steady to you. To a dragonfly, it would strobe visibly. That temporal resolution means a moving target appears to the dragonfly in something closer to slow motion. A fruit fly zigging through the air at full speed looks, from the dragonfly's perspective, like it has plenty of time to plan the intercept. Dragonflies have 4 wings, and each one operates independently. That is the critical detail. A bird has 2 wings that must work in coordinated pairs. A helicopter has 1 main rotor. A dragonfly runs 4 separate airfoils, each attached to its own set of flight muscles in the thorax, each capable of changing its angle, speed, and stroke pattern independently of the other 3. The result is a flight envelope that no other flying animal can match. They can hover in place, motionless, like a helicopter. They can fly backward, They can accelerate from a dead hover to full cruising speed, somewhere around 25 to 35 kilometers per hour depending on the species, in a fraction of a second. They can execute banking turns, sudden stops, and vertical climbs. Some species have been clocked sprinting above 50 kilometers per hour in short bursts. A dragonfly dodging your hand does not flee in a straight line. It can jink sideways, drop altitude, reverse direction, and be 5 body lengths away before your fingers close. If you're finding the engineering behind this insect as wild as I do, take a second to subscribe, because there is an entire kingdom of biological designs this precise. Now back to those wings. The wing mechanics are staggering on a physics level. Researchers using high-speed cameras have filmed dragonflies shifting between flight modes. During hovering, the front and rear wings beat almost in sync but slightly offset, generating a stable vortex that holds the insect in place. During fast-forward flight, the wing beats shift, with the fore and hind wings moving in a counterstroking pattern that maximizes thrust. During prey interception, the wings adjust asymmetrically, one side generating more lift or drag than the other, rolling and pitching the body to steer toward the target. All 4 wings doing different things at different frequencies, governed by a thorax packed with the densest flight musculature relative to body size of any insect. The aerodynamic trick that keeps dragonflies aloft is something engineers have tried to copy for decades. At the leading edge of each wing, dragonflies have a small, thickened ridge called a corrugation pattern. For years, aerodynamicists assumed these bumpy, irregular wings were primitive and inefficient compared to the smooth airfoils humans designed for aircraft. They were wrong. The corrugations create small trapped vortices along the wing surface that reduce drag and increase lift at the low speeds and small scales where dragonflies operate. Aircraft wings stall at low speed. Dragonfly wings do not, because the trapped vortices keep airflow attached to the surface. Engineers at several universities, including groups studying micro-air vehicles, have documented that mimicking dragonfly wing corrugation improves the aerodynamic performance of small-scale drones. Now consider how long this engineering has been running. The oldest dragonfly-like fossils belong to an order called Meganosoptera, and they date to the late Carboniferous period, roughly 300 million years ago. The most famous member, Meganeura, had a wingspan of around 70 centimeters. That is wider than many hawks alive today. These giant insects thrived during a period when atmospheric oxygen levels were significantly higher than today, possibly above 30%, compared to the roughly 21% we breathe now. Higher oxygen concentrations allowed the tracheal breathing system that insects use, a network of tiny tubes that deliver air directly to tissues to support much larger body sizes. When oxygen levels dropped, the giants disappeared. But the dragonfly body plan did not. Modern dragonflies, Order Odonata, are smaller, but they carry the same fundamental architecture. 4. Independently. 2 facet counts, a compact thorax built around flight muscle, a head that can swivel to track prey. The underlying design is virtually the same blueprint that was catching prey in Carboniferous swamps before any dinosaur existed, before any bird flew, before any flower bloomed. 300 million years is a time span that is difficult to put in perspective. The entire age of mammals from the extinction of the non-avian dinosaurs to you reading this is roughly 66 million years. The lineage of dragonflies has been flying for about 5 times longer than mammals have existed. In that stretch, continents split and collided, oceans opened and closed, 5 mass extinctions wiped out vast percentages of life on Earth, and the dragonfly body plan kept going. Evolution does not keep a design because it is pretty or because nothing better came along by chance. Evolution keeps a design because it works so well that every variation performs worse. Sharks have maintained their basic body plan for about 400 million years. Horseshoe crabs for roughly 450 million. Dragonflies belong to that same exclusive tier. Organisms so well fitted to their role that natural selection essentially stopped remodeling them. The compound eyes got a bit smaller. The body shrank. The proportions shifted. But the core system, predictive interception driven by panoramic vision and 4 independent wings, never changed because it never needed to. You are looking at an animal that solved aerial pursuit hunting before the Permian extinction, survived the Great Dying that killed 90% of marine species, outlasted the dinosaurs, outlasted the pterosaurs, outlasted every single flying reptile, and is still catching 95 out of every 100 targets it locks onto. 300 million years of field testing. And the failure rate is still under 5%. No engineer on Earth has built anything with that track record. So the next time a dragonfly hovers near you at a pond, just watch it for a second. Those enormous eyes are processing your movement, the movement of every gnat within 10 meters, and the wind speed across its 4 separate wings, all at once. It has been doing this since before your entire evolutionary lineage crawled out of the water, and it has not needed a single upgrade since. If creatures that break every engineering rule you thought existed are your kind of thing, there are plenty more stories like this on the channel. See you in the next one.